Lecture 9-1, Thermochemistry and Internal Energy. Energy is the capacity to do work or transfer heat. Potential energy is the energy of position. We will be concerned with two types. First, chemical energy is the energy stored within the structural units of chemical substances. That is, it is the energy in the chemical bonds. Second, electrostatic energy is the energy resulting from the interaction of charged particles. Kinetic energy is the energy of motion. Thermal energy is one form of kinetic energy associated with random motion. This energy can be measured with a thermometer and is related to temperature measured in Kelvin. Temperature versus thermal energy. Again, thermal energy is the energy associated with the random motion of atoms and molecules. Thermal energy is an extensive property. To remind you, extensive properties depend upon the amount of matter present. Larger amounts of matter have more thermal energy when at the same temperature. Temperature is a measure of the average thermal energy and is an intensive property. Intensive properties are independent of the amount of matter present. Thus, a milliliter of water at 20 degrees Celsius has the same average thermal energy as a liter of water at 20 degrees Celsius because they have the same temperature. Hence, temperature is not equal to thermal energy. Finally, heat is the transfer of thermal energy between two bodies that are at different temperatures. Thermochemistry is the study of heat change in chemical reactions. We're going to divide the universe into two parts. The system is that specific part of the universe that is of interest in the study. The system is defined by the observer. In the diagram, the system is the blue oval and has an outer boundary. In thermochemistry, the system is usually the chemical process that is being studied. Outside the system are the surroundings. This is the place where most measurements are taken and the thermodynamic changes in the system are inferred from the changes that take place in the surroundings. We have two main thermochemical processes. These are exothermic processes and endothermic processes. In the exothermic process, heat is given from the system to the surroundings. Hence, energy is a product of a chemical reaction or process. For example, the reaction of hydrogen and oxygen to produce water is an exothermic reaction as it gives off energy as a product. Water condensing from the gaseous state to the liquid state is an exothermic process where energy is given as a product of the process. Endothermic processes require heat to be supplied from the surroundings to the system. For example, in the heating of mercury-2 oxide, energy is supplied to cause the decomposition of the mercury-2 oxide into elemental mercury and elemental oxygen. Ice melting is another example of an endothermic process, as energy must be supplied to the chemical process for melting to occur. Units of energy. The SI unit of energy is the joule. It is a derived unit with an underlying set of units of kilograms times meter squared divided by second squared. The calorie with a lowercase c is equivalent to 4.184 joules, and it is exact. This is a defined conversion factor. Also, there are 1,000 calories in one food calorie with an uppercase C. Question: how many joules are in 250 calories? That is, food calories. Take 250 calories and multiply by 1,000 little calories per big calorie. Then multiply by 4.184 joules per 1 calorie. And the final answer is 1,046,000 joules. Thermochemical systems. There are 3 types of thermochemical systems: open, closed, and isolated. The open system can exchange both mass and energy with its surroundings. The closed system can only exchange energy with its surroundings, and there is no exchange of mass. The isolated system does not exchange either mass or energy with its surroundings. If we can create an isolated system, we can more easily study thermochemical processes. In thermodynamics, state functions are properties that are determined by the state of the system, regardless of how that condition was achieved. Basically, what this means is that to know what has happened thermodynamically, we only need to know the initial and final states of the system. The path of thermodynamic changes does not influence the overall change of the system and any calculation related to that change. Examples of state functions include energy, pressure, volume, and temperature. In the picture, if we assume that each hiker has the same weight, the potential energy change for each is the same after the climb to the top, even though they took different paths. The law of conservation of energy. The first law of thermodynamics states that energy can be converted from one form to another, but it cannot be created or destroyed. Mathematically, this means that the change in energy of the system plus the change in energy of the surroundings must equal 0. Put it in another way, the change in energy of the system is opposite the change in energy of the surroundings. For example, in the combustion of propane, the chemical energy lost by combustion, which is the system, equals the energy gained by the surrounding air, which is the surroundings. Another form of the first law of thermodynamics for the change in energy of the system. The change in internal energy for the system equals Q, the heat exchange between the system and the surroundings, plus W, the work done on or by the system. For a gas expanding against constant pressure, work equals negative 101.325 times pressure times change in volume. Work and heat and their signs. If heat is absorbed by the system, which is an endothermic process, Q is positive. If heat is released by the system, which is an exothermic process, Q is negative. When work is done by the surroundings on the system, for example, a volume decrease in the system, W is positive. When work is done by the system on the surroundings, for example, a volume increase by the system, W is negative. Calculations. What is the change in internal energy for a system which absorbs 369 joules of heat from the surroundings and does 593 joules of work on the surroundings? The equation is the change in internal energy delta U equals heat, Q, plus work, W. Since the system absorbs heat, the value for Q is positive, plus 369 joules. Since the system does work on the surroundings, the value for W is negative, minus 593 joules. The change for internal energy is 369 minus 593, which equals negative 224 joules. For the second problem, the change in internal energy is 438 kilojoules. The system does 529 kilojoules of work on the surroundings. What is the heat for the system? Since the work is on the surroundings, the value of W is negative 529 kilojoules. Thus we have 438 kilojoules equals Q minus 529 kilojoules. Solving for heat, we get Q equals 438 plus 529, which equals 967 kilojoules. Internal energy is a state function. As a result, all we need to know is the initial and final states. Internal energy has two components, kinetic energy and potential energy. Kinetic energy has to do with the motion of the atoms and molecules. Potential energy deals with the attractive and repulsive interactions between chemical species. Changes in internal energy cannot be calculated with certainty. However, changes in the energy of the system can be determined experimentally. The final state in a chemical reaction is the energy content of the products. The initial state in a chemical reaction is the energy content of the reactants. We can determine the energy change of the reactants and products, but cannot determine the absolute value of the energy. Thus, the internal energy change of the system equals the internal energy change of the products minus the internal energy change of the reactants. In the example, the internal energy change of the reaction of magnesium and oxygen to make magnesium oxide is the change in energy of 2 moles of magnesium oxide minus the change in energy of 2 moles of magnesium and 1 mole of oxygen. This concept of the change in energy of the system being equal to the change in energy of the products minus the change in energy of the reactants will be used in many state functions related to the change in energy of a chemical reaction.